So this is week 13, video number 2, and in this video we're going to talk a little bit about programming and how do you program a computer and how do computers work and what is programming. And all through, or part of the way through the semester, we've been doing some programming assignments. And so inside of Canvas, I believe, in our assignments, we've had a few programming assignments, and so I'm just going to look down here and see where we have done some of those. Programming variables in printing, programming variables in math, programming conditional logic. So we did a few programming assignments. So you got a little bit of a taste of basics of programming. And programming, when we create a program for a computer, what we're doing is we're giving the computer instructions. So a program is nothing more than a set of instructions. We're programming a computer what to do. So we're just going to start at the basics here and talk about what is a program and programming and that kind of a deal. So a program is a set of instructions. And with computers, there's hardware and then there's software, right? And so we need the hardware. We need the actual physical hardware, right? The physical stuff, the circuits, the machine. But then we also have to write instructions or programs that tell that machine how to work and what to do. And so that's what software is. So software is another word for a program. And we need to be able to create that hardware, and then we also need to have software that's been created that runs on that hardware. And so those two components, the hardware and the software, are two essential aspects that need each other to work together to create this computing device, these machines with which we interact and get information, right? Take data and turn it into information. And so writing instructions for a computer is what programming is all about. And telling the computer what to do. And so, I'm just kind of thinking about my notes here and what to say. But, the instructions that we write are sometimes referred to as algorithms. And so algorithms are just solutions to some sort of a problem. It's an algorithm. And if we look up the word algorithm to see what it says, and I don't know what this is going to say, but if we say define algorithm, it's a process or a set of rules to be followed in calculations or other problem-solving operations, especially in a computer. So you can have, in particular, an algorithm refers to a problem-solving method, set of instructions for a computer to solve some problem. That's what an algorithm is. But you could also think of algorithms for solving any problem. So, maybe you're like, hey, how can I become, have a really successful restaurant in my town? And you might come up with a set of steps and a sequence of events that you're going to do to create a great restaurant franchise in your town. And so then later somebody might be like, well, what was the algorithm for success? Or you might say, my algorithm for success was great customer service. Right? So these are the things I did to realize success. And that would be your algorithm, right? It's a solution to a problem. And so that's something you hear often when we talk about programs. They're solutions to problems. And then we refer to those as algorithms. And often computers, when we program them, they're very literal. And so we have to specifically tell them what to do. And so we discussed this last week a little bit. We talked about machine learning and artificial intelligence. So traditionally, programs have been very explicit. If this, then do that, right? We just give them very precise instructions. But with machine learning and artificial intelligence, increasingly computers were just saying, we want this outcome, figure out how to achieve that outcome with all these variables which can be adjusted. What's the best mix in different quantities of these different variables to achieve the desired outcome. And so in that sense, the computers, when we program them today with machine learning, we aren't specifically telling them exactly what to do. And instead, we aren't giving them explicit instructions. And instead, we're kind of saying, look, this is the outcome. Figure out how to achieve the best desirable outcome. But traditional programming has been very explicit. And so, for example, if I wanted to make toast or have a robot make toast, I'd have to tell the robot I couldn't say get bread and put it in the toaster. Like for you and I, we understand what that means. But for a computer, they would take the whole loaf of bread and then try to put it in the toaster, right? Like we had to have to say, you know, turn right, identify bread, you know, is there a plastic bag around bread? Yes, no. If yes, open plastic bag. You know, is there a slice of bread? If yes, take slice of bread and put it in slot of toaster. All right. Is there another slice of bread? If yes, take piece of bread and put it in another empty slot of the. You know, you have to be really explicit with computers, with traditional programming. So you know, those are kind of the basics of programming. There's a little bit of a joke, and this programmer died, and they went to his house and they found him dead in the shower, and he's holding a bottle of shampoo, and on the bottle of shampoo the instructions said, wet hair, apply shampoo, wait 2 minutes, rinse, repeat. And so this programmer, who's very literal and just explicitly followed instructions, just kept repeating that process until he died in the shower, because there was no exit from that infinite loop. So that is known as an infinite loop in programming, where the instructions just keep going over and over. And if you look at Apple's headquarters, right, it is at Apple Park Way. It used to be infinite loop, I thought. Let's do this. Apple's headquarters, one infinite loop. So here we go. There we go. Apple Infinite Loop. Right, so that's the address, at least, you know, their retail store and stuff. It's one infinite loop. So that's their address. And when we look at how computers execute instructions, so computers, when you give a computer a set of instructions, they execute those instructions. This is called the flow of the control, you know, or control flow. This is the way that the computer reads the instructions. They start at the top and they read them just straight from top to bottom, and that's known as sequential or sequence. They just go in sequence from top to bottom. But then sometimes they'll hit conditional logic, where if condition is one thing, do this, otherwise do that, right? And so they'll be going in sequence, and then they hit conditional logic, and they'll go one way or the other based upon conditions. So we have sequence, we have conditional logic, and then sometimes it'll hit an iteration or loop. For every student in the class, calculate their grade. And so for each student in the class, it'll then loop through a cycle of instructions and do something. So those are the three control structures in programming. The computer works in sequence, reads from top to bottom until it hits either conditional logic, an if-then statement, go this way or go that way, or a loop, right? Or a loop. So those are known as the control structures. And then we have bugs. And so a bug is an error in a program. And I think we might have already mentioned this in this class, but Grace Hopper, you know, bug. So the original computers were big, and they had vacuum tubes, and they're warm, and like a moth flew into the computer, or they would fly into the computer, and then they would kind of die in there, and they'd have to go in and literally pull the bugs out of the computer or debug the computer. And so first actual case of bug being found, right? They pulled this moth out and taped it into the log. And so still to this day, when you find errors in a computer or in programming, it's called debugging the computer because of that. Here's a visual representation of the three different control structures, or two of them. So this is sequence. Here's selection or conditional. If this, do that. If not, do this. And then here's loop. Right? Just keep looping over this procedure so long as a condition is true. And then when it's no longer true, exit the loop, right? So you're not in an infinite loop. So it's kind of a little bit of an intro to programming. And when you look at how programming has evolved over time, there's been an evolution in the way code has been written. And so back when I was in junior high and, you know, I learned basic programming, code was all written on one page, a lot of it, and it was really hard to follow. And the page would be many lines long, and then in the code you would have go-to statements. So like at line 80, you might say, go to line 500. And that created this really obtuse logic, which is really difficult to follow. And so following threads of logic about what happens in different situations was kind of like following a strand of spaghetti in a spaghetti bowl. It was really hard to do. And so they called it spaghetti code. It's just complicated and hard to follow any of the logic. And so what they did is they started breaking programs up into procedures. And they called this procedural programming or structured programming. And so they'd have a procedure like, oh, now we want to do this. Go run this chunk of code over here for this procedure. Or go run this chunk of code over here for that procedure, and then return back to the main program. And so that was like creating a more structured approach to programming with these different procedures. So they called that procedural programming or structured programming. And let's see what's all is said on here. So you could pause the video and read this. The interesting thing to point out here is it kind of followed this top-down design approach, which is taking a large problem, breaking it into small manageable chunks, and then writing little procedures, little chunks of code for each of those procedures, right? And then calling those little chunks of code when you needed them to run. And so that was the idea there. And then the next evolution in programming was kind of like object-oriented programming. And object-oriented programming is where those procedures, programmers started to create chunks of code which could be replicated to represent objects in the real world. So if you're creating a video game, you would write the code for like a car in the video game one time, and then anytime you needed code for a car, you just create an instance, right? You'd say, oh, use car code here, but I'm going to change some properties or some variables. This car will be red, that one will be blue. But then if you ever had to modify the main object, the main class of something, you just change it in one place instead of having, multiple things where you have to change it. And then that one place changes and all the instances are updated, or, all the cars that have been built off of that chunk of code, are updated. So that was kind of like this idea of using code, programming code to represent objects in the real world, like structuring your code so that, they represented, the code was for objects in the real world was like, written like that's for a car, that's for a person, that was object-oriented programming. So it's kind of like structured or procedural programming. So here's an example of that. We'd create a class called bicycles, and then we'd create instances of bicycles, right? And there'd be attributes like, things you could change about the car, like the color or the size. And then there'd be methods, things that a car could do. And then you create instances, and and then each instance would you'd be able to change the properties, the attributes of the bike, and then they'd also inherit all the methods, all the things that it can do. When you program, we create variables too. So variables allow us to store information, usually related to some user using the program. And so like if you log in at a website, it'll ask you for your name when you create your account, and then your name is stored as a variable. And then when we write code, we say it's kind of like a form letter, and display username here, and then when you're using it, it displays your name there, right? And so that's kind of like a variable. It's like we'll put in the little variable for the username there, and then whatever the username is for the person using it gets filled in there, and that's kind of what a variable is. We also have variables for like, so that'd be like for a name. And then there's a variable for, we want to like maybe do math. And so you enter a number, we have to store that number. So that'll be like, number 1, number 2, number 3, and then we add them all up and we store those numbers in variables. They're little containers that hold values. That's what variables are. So we talked about the systems development lifecycle. Then there's also the programming development lifecycle. They're both pretty much the same. They're problem-solving processes. You identify a problem, you come up with a potential solution, you build the solution, you implement the solution, you evaluate the implementation to see if it's working the way you wanted. That's kind of the PDLC. So problem analysis, program design, program coding, debugging and testing, implementation and maintenance. That's PDLC. You really want to, if you become a programmer, you kind of get used to how to design programs, and, you want to make sure they're designed well. That's one of the most important things about programming. You gain that skill kind of like in any craft by being an apprentice and working at it, and over time you just get better at it. But some of the things you avoid are, making sure that there aren't errors. So there could be logic errors, and then there could also be syntax errors. So logic error would be like 2 plus 3 is equal to 7. So your program ran, but it gave you the wrong error. It gave you the wrong result, right? 2 plus 3 doesn't equal 7. 2 plus 3 equals 5. So that's a logic error if it gave you 7. And a syntax error would just be that you typed in the wrong, information when you're writing the program, and the program won't even run. You didn't spell something correctly. So you avoid those things and create better structure the longer you go. So you could create flowcharts like this to kind of detail out, what's going to happen, what's the logic of your program. You could also write in a similar way, write your stuff out in like pseudocode, they call it. Like, here's kind of what I want to code when I get into actually coding. Here's the logic. And then, actually coding it, right? You want to choose which language you use. So different languages are good for different purposes. And we talked about this before, but you could go to Stack Overflow Developer Survey, and you can look at like how popular different languages are and how much they pay. But the language that you use for creating a video game would probably be like C or C++. Let's look. Technology. Most popular technologies. Right? So here's C and C++ and C#. Right? Like these would be more for operating systems, and for video games, they're going to run really fast. This is for databases. This is more for web, as is this, right? And Go is good systems level design for the back end of web. HTML and CSS is for web. And so the top three are for web. This could be more data analysis and making your computer do stuff, and working with, what do they call those little computers? Pi computers? I can't remember the name right now. But programming little robots and things like that might be done in Python. Anyhow, so there's different languages for different things, and you want to see which languages are popular when you're learning a language, and what those different languages are used for, because different languages have different purposes. Then once you've written your program, so there's machine language, which is the language computers operate in, which is zeros and ones. And then above that, there's assembly language. That's the second generation language. And then above that, there's third generation languages, which are most programming languages. And there's fourth generation languages, which is like SQL, which is a little bit closer to natural language. And then fifth generation is natural language, which is what we speak. And so when you program in a third gen language, you then need to get that down to zeros and ones, that the computer uses it, because you can't write the code in zeros and ones. Our brains don't work that way. So we have to say, if this and, variable equals and all that. But then when we're done, we compile or translate what we wrote down to zeros and ones. So that's called compiling or translating when we do that. So that's a little bit of an introduction to programming. It's a great skill to have, and it's a very good paying occupation. It is kind of like akin to playing an instrument. And so you could sit down and you could learn piano for a year or two, and you can play a couple songs, and that's cool. But if you really want to be a crafts person, you need to devote yourself to it. And there's kind of like no hobbyist kind of level to it, in my opinion. You either do it, and that's what you do for a living, like being a musician, right? And you practice it and you're doing it every day, or you don't do it because it's full on, it's demanding, but there's a lot of opportunity in it. So if it calls to you, you can make it your craft, and you could do it every day, and you could become really good at it. You don't have to be necessarily, super genius or anything like that at all. It's just something you have to enjoy, sitting at the computer 8 hours a day, right? And then if you do that for many years, you become really good at it. But that's what you have to choose to do with your life. So that's a little introduction to programming. In the next video, we'll take a look at chapter 13 in the textbook.